main part of the energy that is released from a core collapse supernova. So listen to this bookkeeping. So the energy associated with the core collapse supernova is as follows. Neutrino energy, so the energy carried out by neutrinos. Oh, Suji mama, good girl. Good girl, Suji. Suji's drinking water, so I'm encouraging her. Good girl, my baby. So, neutrino energy. The energy carried out by neutrinos is 10 to the 46 joules. That's a lot. Kinetic energy of ejected gas, 10 to the 44 joules. Photon energy, 10 to the 42 joules. So photon energy is actually the least. This energy comes from the gravitational potential energy of the pre-collapse core. A neutron star has gravitational potential energy of -3 times 10 to the 46 joules. This is about 10% of the rest energy of a neutron star, which is 3 times 10 to the 47 joules. Thus, compressing matter into a neutron star is a fairly efficient way of converting its mass into energy. At maximum luminosity, the supernova emits photons with a luminosity of around 10 to the 9 solar luminosities. However, the supernova decreases in luminosity by a factor of 100 over a few months. So if we see Betelgeuse supernova, Betelgeuse is a red giant. We expect it to supernova or die. At first, you would see a very bright star as in a bright spot, a bright star. I'm saying like this because it's a supernova. But then over the course of a few months, the luminosity should be kind of going down, you know. Supernovae are bright but brief-lived phenomena. We looked at gamma ray bursts, remember, even more extreme events in the sky, and they are super transient. Gamma ray bursts, the typical length time period of a gamma ray burst is even shorter. It's of the order of like seconds, you know. Of course, there's some more details that we also discussed about that, but you know. An interesting tidbit of information is that the nearest star, oh, here we go. I forgot. They're about to talk about Betelgeuse. An interesting tidbit of information is that the nearest star with mass of greater than 7 solar masses. So Betelgeuse has a mass of over 7 solar masses. So it's a giant. And that's like a terminology in the life cycle of a star. What did you say creates gamma ray bursts? So gamma ray bursts, depending on the type of gamma ray burst, if it's a long gamma ray burst, it is basically from a hypernova, like a super big supernova. So the stuff we're talking about now, but like even more extreme. That's what makes a long GRB, long gamma ray burst. And then short gamma ray burst is from mergers of, so like super, it's basically from an explosion, but it depends like what causes the explosion, right? So the explosion in the case of a long gamma ray burst is either a hypernova, or in the case of a short gamma ray burst is basically a neutron star merger or a neutron star black hole merger. So like two neutron stars in a binary doing a dance together, revolving around each other, losing energy, will finally collide. And when it collides, there's massive amounts of energy released, an explosion, lots of drama. That's basically going to give you a short gamma ray burst. Or a neutron star black hole binary. Oftentimes, these things are in binaries. They're like a couple exploding together eventually. What a couple. So, Betelgeuse, speaking of supernova, so Betelgeuse is a giant. It has a mass of greater than 7 solar masses, and it's at a distance of only 130 parsecs. When it becomes a supernova, any millennium now, pretty much Betelgeuse, when I was in undergrad,